Thank you all. Welcome to Transcend's climate change webinar. Unfortunately, Adam had something come up and wasn't able to join, so you get me as one of your hosts, along with Rudy as well. So just want to say welcome. So like I said, my name is Remy Monahan on the business development team with Transcend. I'm joined by Rudy, one of our process engineers, and we're here to discuss how we can help prepare our treatment plants for an unpredictable future in the face of climate change starting today. So I will go ahead and share my screen, have a short PowerPoint for you. All right. So for those of you who are unfamiliar with Transcend, we are a design automation software that helps to expedite the preliminary engineering process of treatment facilities. So we help our clients in a few different ways when it comes to the conceptual engineering as well as automating proposals. So when it comes to climate change, we may think that we have an idea of what's going to happen in the future. In reality, we have no clue. When it comes to things like regulations, emerging contaminants, and technology advances, there's so much variability when it comes to evaluating our treatment plants. So I don't need to be the one to tell you that there just simply is not enough time nor budget to consider all the different scenarios during the capital planning and conceptual design phases. But we want to start to build a sustainable future, we need to start looking at these options now. So what Transcend does is allows you the opportunity to evaluate these different options very quickly. So you take an existing wastewater treatment plant, and immediately there are a few different options that you can start to evaluate, including temperature range, some technology options, as well as some load range. But within those, there are other categories and other factors that you need to also evaluate, including when it comes to temperature range, specifically when it comes to climate change, a lot of different scenarios when it comes to the temperature ranges that could be affecting your treatment plant. So immediately the web starts to grow. But when you look at these even further, when it comes to something like population growth, there are more scenarios. And like I said, there's not enough time, not enough budget to evaluate every single one of these. But if we want to start designing these for a sustainable future, it's really critical that we start to take these into consideration today. So Transcend allows you in a matter of hours to run all these different scenarios in order to then compare and meet your treatment plant goals. So I'm going to kick this now over to Rudy Boda, who is one of our process engineers, and she is going to share with you our tool, give a quick demo, which displays how you can actually run these different evaluations for your treatment plant. So as Rudy is pulling up her screen, just a few housekeeping things. If you have any questions, feel free to put them in the chat or go ahead and come off mute if you feel comfortable, and we will help to answer those questions for you.
Thanks so much, Remy, and welcome everybody. My name is Rudy Boda. I'm a process engineer at Transcend, and as Remy mentioned, we're talking about climate change today, and so I'm going to take you through a quick presentation and then a demonstration. So the presentation is about the following items. I'm going to have a quick overview of the tool, conceptually, what is it made out of? And then when we think about climate change, some of the first few concepts that come to mind is temperature change, as well as flow change, as we've been seeing very high rainfalls in some areas. And so I'll be speaking a bit about how that is incorporated into our designs. And then we'll go through a demonstration of the user interface and the outputs, and speak a little bit more detail on what the design generator can do in terms of outputs and feasibility studies. So let's jump right in. Starting off with just a high-level overview of what is happening in the model. So we start off with data input and validation, and you'll get to see we're taking a range of data, but focusing really on the flows, the influent concentrations, and the effluent limits. And as the effluent limits are getting stricter and changing, it's interesting to analyze how that impacts our treatment plants. So you can play around with different inputs in that regard. And then within the user interface, we have an algorithmic validation to check, are these reasonable inputs? Are they what you would expect in a wastewater? So we're not looking for a peak flow that's less than our average, and we're not going to accept values that are very far out of a domestic wastewater range. And so we check those and we let you know, okay, maybe you've made a typo, you've switched, BOD or COD. And so we check those before you run your process so we can have a successful result. And then once you've started your design, we go through a number of steps, process, and then mechanical, architectural, and civil, and the output documents. And so we start with the process design. We base these process designs on international standards. So a lot of the calculations are based on Metcalfe and Eddy, which most of you will be familiar with if you're working in the wastewater treatment space. And initial calculations are done on a steady state sort of algebraic level to initiate the process of then further going into a dynamic simulation. So we check on a dynamic temperature range over a long simulation of a year with diurnal flow patterns to see if that algebraic calculation is reasonable. And if it is not, we go back and we change something like the reactor volumes, the dissolved oxygen concentrations, and we rerun that simulation until we found something that works. And then we go ahead and size the units. And these process calculations then inform the further calculations of equipment sizing and selection, as well as the OPEX calculations for how much power those equipment are using. And we also then produce architectural or civil drawings, so layout drawings, as well as 3D models, which you can then download in editable formats. So all our documents are downloadable in editable formats. And that means you can use this as a basis to develop your design to something more detailed. So this is a preliminary design level, but it does give you the option to then quickly take it to the next step. And I'll take you through the output documents. Some of these include a technical description of the data you've inputted, any assumptions we've made in the model, and what the output data is as well. So that's a nice report. There's a equipment list, a load list, OPEX sheet, the architectural drawings, as I said, and as well as a bill of quantities. So I'll go through all of those as well. Just wanted to stop here. Are there any questions on the sort of overview of the model and how it's working? Okay, we'll go ahead. Just stop me if there are any questions, or feel free to post them in the chat as we go. So I just wanted to focus on this element of flow variation, as we've spoken about in terms of climate change. So what is actually going into our wastewater treatment works? Well, we have, this is just a simplification really. We have domestic wastewater, and it's varies during the day. So we have this diurnal flow pattern you may be familiar with, and it's quite important to take into consideration these peaks in our designs of wastewater treatment works for hydraulic purposes of sizing hydraulic units, but also for the aeration demands in the biological systems, if we are using aeration. And to accommodate those peak amounts, we need to size the equipment to handle that peak. So in domestic wastewater, there may not be significant peaks in a large population, but as we add industrial flows, there may be different peaks overlapping, causing even larger peaks. And then there's also rainfall that can ingress into the sewers. And as we spoke about in terms of climate change, we're seeing these rainfall events actually getting more severe in shorter periods. So we have higher rainfall in a short amount of time. That makes our peak much higher. And to accommodate that, we need to start thinking about that in our designs. So how does the design generator take those peak flows into account? Well, we have many options for you to provide this data. We base a large amount of the design on the design average flow rate. So this is what you choose to design your plant for. So maybe you've projected into the future that in the future you will need a 200 megaliter per day plant. That's our maximum at the moment, but we are looking at expanding it. And you can insert that as your design average flow. So we use that to size the biological system, produce OPEX results. So how much sludge you'll have to dispose of, how much airflow you'll use on average. But then the important thing here is the peak flows. And we provide so many different options because everybody has different data. And so if you have, the peak weekly flow or peak daily flow or peak hourly flow, you can put that in and we can use that. So we provide a space for two different peaks, essentially. One for your dry weather. So that's when it's not raining. And that is something that will influence the wastewater treatment works on a daily basis. So that's what we call peak dry weather flow. And we use that to create that diurnal flow pattern we just saw, as well as to size the blowers for the peak airflow and as I said, blower sizing and the peak airflow. Then we have wet weather flow. So these are not necessarily happening every day, but in your rainy season, you'll have a day of rain if that happens in your city, like in my city, or maybe just a couple of hours. And that can influence that peak flow that's coming through your plant. And that is what we design the hydraulic flow in the unit sizing for. And as we're working on a preliminary level, sometimes we don't have all of this data. And so what's great about the design generator is we try and help you out with whatever data you don't have. So there's only really a few values you have to fill in, and these peak flows are not one of them. So if you don't have any peak flow data, that's all right. We take an estimate of your biological oxygen demand in the influent and your average design flow. And we can then estimate from a large flow that you may be accommodating a high population, and then there are lower peaks. Or if you have a very small flow, you may have a small population, therefore you have quite high peaks. If we look at the temperature side of things, so we offer also the option of putting in a minimum and a maximum temperature. And this is also going to impact the size of your biological system. If we're using oxygen blowers in the biological system, then the dissolved oxygen in water decreases as the temperature is increasing, as well as an increase in temperature is linked to higher humidity and also lower concentrations of oxygen in the air. So you can see from these two graphs. And that means your blowers are going to be working a lot harder, using more energy to get the same amount of oxygen into your reactor. And so this is going to influence the sizing of your blowers and the amount of peak airflow they will have to create. So that was just a little bit of a background on what the technical elements are I'm going to be highlighting in the model. There's a lot in the model, and so it's difficult to touch on it all. But as we're focusing on climate change today, I thought I'd just mention these in particular. Before I jump over into the demonstration, I'm just checking if there are any questions yet.
No questions in the chat right now, so feel free to put them in there if you have any.
Great. So we're going to jump into the Transcend design generator. This is just an image of your landing page as you arrive. And I'm now going to just switch over to that side. There we go. So this is our dashboard for our design generator. And you can see some of the previous projects we've run here. And if you'd like to start a new project, click up here on the orange button.
Hey, Rudy.
Yes.
As you're getting that pulled up, there is a question. So says, hi, for smaller facilities, surface aeration may be preferred. Can one select these instead of blowers?
That's a great question. At the moment, our generic version of our model doesn't include any surface aerators. However, if that is something that your company would like to include, we can certainly adapt each sort of dashboard per company, and we do that quite regularly. So if there's a particular piece of equipment that your company uses, or there's a different way that you design a certain process unit, there are many ways that we can adapt. So as we go through this, you'll see these are just the generic ones, and we kind of keep it a bit limited for this version, which is often available quite free. So it's maybe being used by people who are not necessarily engineers. And so we don't want them putting in all sorts of different values where they don't understand what's happening. And so we've simplified it in a way. But in the background, there are a lot of technical details that we can bring to the foreground. So if there's something here that you would like and you don't see on the dashboard, it is absolutely possible to just bring it forward. It could just be in the background. But at the moment, there aren't surface aerators, but it's something we could include. I hope that answers the question. Great. So this is our first page of the tool. And here's just some project information, your utility name, the project name you'd like to choose. And if you're in a place that uses imperial units, you're welcome to select them here. I'm based in South Africa, so I'm just going to use that as an example, but you can include your plant's location. You can also then select whether you have an existing site or not. So if you select that you do have an existing site and you'd like to reuse some of these assets, then you will be presented with a Google image on the next page, and you can select those units. So you can reuse your existing process units, or if you don't have existing process units, you can just select the site, and then all the civil drawings will be placed on that site. I'm going to continue without this, as I'd like to focus on the flow and temperature for this specific demonstration. So the next item here is then your input data. So we have flow, influent, and effluent inputs. With the flows, we only have to include temperatures and average flow. But if there is the interest in exploring peak flows, as we've been discussing. Here you can really specify. We also provide typical values. So these are linked to your region. So these are typical for South Africa, and I'm going to use these values. And for our average flow, I'm going to use a plant of, let's say, 40 megaliters per day. And now I can include any peak flows I need. Quite common peak flow is about double the average flow in a diurnal pattern. This is what's common for my area, might be different for yours. And then here we can choose one of the wet flow peaks. So you don't have to include them all. If you do have them all, that's great. Whichever one you insert will be used. So let's say, for example, in a rainy day, we get quite a lot of rain in a day, and it might be about 4 times your average flow. Another interesting feature that I'm going to go into a bit more detail after this, and it's very helpful in climate events such as high rainfall, is a bypass system. This allows you to bypass your flow from 3 different points in the wastewater treatment works. And you might be asking why you would want to use something like this. Well, it's actually used in Cape Town, where I live. One of the wastewater treatment works has been surrounded by city, as it was built very long time ago. And so there's no longer space to expand it. So they've created a bypass to a wastewater treatment works further out of the city. And so they only use primary treatment and bypass all of the main biology and the disinfection, and then send the treatment out to a second wastewater treatment works. So this is the example that we have here. We're going to send it through the primary treatment, but bypass main biology and disinfection. So I'll include that here. You can use either a pumped bypass or an overflow. So if you include pumped, whatever value you put in here will be the fixed value that you're bypassing. And if you choose overflow, you will keep this amount, and anything more than this amount will be bypassed. So let's, for example, use 70 megaliters per day, 70,000 cubics per day. And so anything more than that will be bypassed from the secondary to the disinfection. Just going to pause a little bit here. This is quite an interesting concept. I don't know if there are any specific questions on this. Okay.
I'm not sure if we have any questions on that, but we do have one in the chat that says, from your experience, which is more power consuming for air blowers, in conventional activated sludge or an extended aeration?
I think the extended aeration is likely to use more more power. You're using a very long sludge age, and so it's breaking down particulate matter that take a very long time to break down. But we could test it in the system and have a look. Sure, it's it depends on a number of factors. You'd need to compare it, keeping everything the same.
Of course, thank you.
So to save those results, I'm clicking next onto the next page here. And here, the influent flow data. The red stars are indicating the ones that we have to include. And I'm going to use these typical values from the region. Of course, you could, instead of using TKN, you could choose to provide ammonia instead, or as well, if you have the data available. And if you don't, we will create a calculation in the background to estimate it. Next, we're on to the effluent limits. So these, again, the required ones I will fill in there. If you have more effluent limits that you'd like to specify, you can include them. Just for example, I'll include the TN as well, and the phosphorus. And here you can choose your compliance requirements. So if your compliance is on a monthly average basis or daily average basis, you can indicate that here. And now we go to the preferences. So this is where you are able to choose which components of the process you would like in your treatment plant. There are options to let the calculation decide, for example, for the grit removal and flow equalization. So if you select this option for the flow equalization, when there's a very high peak, then it will provide flow equalization to balance out the size of the other downstream units. Or if you specifically want flow equalization, you can override and say, no matter what the peak is, you want flow equalization. You can also choose your primary treatment. So there are primary clarifiers, filters, and an upflow anaerobic sludge bed reactor. So for example, I'm just clicking a primary clarifier. And then the technologies that are offered here are the CAS and the SBR. And the reason why there are only two here is because we chose a bypass. So the bypass is only available for these two technologies. But if you'd like a different technology, you can always go back. So I just wanted to show you that, for example, if we go back to our data and we remove our bypass, we can then remember to click next as it saves your data. We can then head back to our preferences and you'll see there are a number of technologies available, and you can choose more than one and they will produce a set of outputs for each of these main biologies. So we can run the model and compare how it will look if we have an conventional activated sludge system versus an MBR or an MBBR, IFAS or SBR system. Just going to reselect my primary clarifier there. If you have a specific number of trains that you would like to select for the biology, you can choose that. If you have a preference for chemical removal, you can indicate that. And you can choose whether to include the sludge line, an anaerobic digester, and disinfection. Are there any questions there, Remy?
Yes, we have one in the chat. So since we are focused on climate change today, have you noticed any trend of increasing or decrease of the effluent wastewater temperature?
I haven't personally, but I think that it would be highly likely to occur, especially as our summers get hotter. So I think it's very likely. I haven't seen any specific examples though.
Thank you.
So once you've chosen which items you would like in your design, they will appear. So there'll be a page here for each of your chosen main biologies and primary treatment. And you can then specify any specific design parameters for each of these process units. So if you'd like to use one that's different from the standard, so here the information block tells you that the standard range is between 1.5 and 4. And if you'd like to use something other than the default value, you can input it here. So for example, for the activated sludge, we can choose a minimum aerobic sludge retention time. And we could also choose whether we would like biological phosphate removal. And so let's, for example, include that. We can then also choose a particular configuration. I'm going to choose the UCT configuration. I'm familiar with this one. And we can specify some parameters associated with clarifiers as well as mixed liquor suspended solids concentration, or the side water depth. So if you'd like a really deep reactor or a very shallow reactor, if you're planning on using surface aeration, for example, you can specify that here. So let's, for example, use quite a shallow reactor. And the same can be applied for all the different technologies. If you'd like to specify something specific, you can, but most requirements are not, most of these inputs are not required. And so you could just click through to use the default values, which are industry standards. And that's it. You've created you've provided your data and chosen your preferences. And then all that's left is to run the design. So this one's running at the moment, but if we have a look at one that's already finished, it'll look like this blue dot here, and you would be able to click on this icon and see all the output documents over here, where you can view them in the browser. You can download PDFs, and download editables is also available if you have a subscription. So I'm just going to take you through a few of these output documents. All
right, Rudy, as you're pulling those up, we actually have a few questions.
Great.
So does one have a chance to vary the settling SVI by season to see if the settling is okay throughout the year? Or maybe we have to use the worst case scenario?
So that is varied throughout the year. So as I mentioned at the beginning, we do a dynamic simulation as well. And that is varying a couple of values over an entire year or more than a year's simulation. And those values that are varied are the temperature and the SVI. And so it is varied throughout the year through the seasons, as would be normal for a seasonal flow.
Thank you. And the other one actually had to do with SVI as well. So Hani, please let me know if that answered your question, and then we should be good to go, Rudy.
Great. So these are some of the output documents that you'll find. The design basis is just a summary of the inputs and assumptions we've made in the model. So these are the influent flows, influent concentrations, effluent parameters, and in the design, if there are any characters we didn't include, for example, we didn't maybe specify orthophosphate, but that's been calculated in the background, it will then list that here. And then the next document, the technical description, one of my favorites, is really the comprehensive description of all the preferences we've chosen and the design parameters associated with each process unit. So there's an introduction. It actually gives you a description of where the flow is going, through which process units, if it's being diverted, bypassed, what is happening in the sequencing batch reactor, for example, here, whether there's biological phosphorus removal, etc. So that's quite a helpful document that you don't then have to, as a process engineer, write for each and every design that you would like to run. There's a quick description, summary of the basis of design, so just influent and effluent limits, and then quite a lot of detail on screening, grit removal, equalization tanks, your reactor and sizing of the reactor, and exactly the flow pattern. For this example, it's a sequence batch reactor, and the aeration demand, any chemical phosphorus removal, disinfection, sludge management. The whole design of the plant is listed here. Next, we have a equipment list. So this lists all the equipment that's required in the plant. It provides a bit of details and specification and the material type, any duty or standby units. So that's very helpful in terms of CapEx and sizing. We also have instrumentation list. So these are the online monitoring units, level switches and transmitters, with a bit of specification detail as well. There's a load list to indicate the power consumption, installed power, and average daily consumed power of each of the pieces of equipment. We have an OPEX table, which nicely summarizes any of the outputs, so electricity consumption, chemicals, waste disposal, and then these can easily be taken into an analysis of which option to choose going forward. In terms of the civil documents, this is the 3D rendering that is an output document in Revit. And so each of these structures could then be changed, and you could rearrange them if you're not happy with the layout. This is also provided in a site layout format. And there's also a very short bill of quantities. It's a summary of all the capital requirements in terms of civil structures. I don't know if there were any questions about the output document.
I don't see any in the chat right now. One clarification on what do you expect for better sludge settability in hot or cold areas?
It's going to depend on the sludge types and so on. There's a lot of different situations that can occur depending on your biology upstream and before your settlers, or in your primary settling, composition of the wastewater. It's a little bit difficult to say on a general basis.
Okay, thank you. And does the process summary give a total energy consumption for the design?
Yes, so our OPEX summary, as I showed just briefly, I'll go back there quickly. So there is a total electricity consumption per day. So this is on average consumption. And then if you have a look at the load list, you could have a breakdown of that as well. So there's the average consumed power for each unit, as well as the installed power. And this, of course, takes into account this duty standby. So we won't be consuming power from all our process units all the time. Some are there on standby to be the backup. I hope that answered the questions.
Thank you. That is our last question in the chat. So if anyone has any more, feel free to come off mute or put it in the chat. Yes, I will share a link to a free design. So With this link, you'll be able to run one free design credit. And then, as Rudy said, for more credits and the ability to download more of the editable formats, there is a subscription fee. So with that link, everyone has access to a free design credit.
Thanks. Thanks, Remy. If anybody's interested in a little bit more detail, these are just a few of the process units that I mentioned as we were going through the demonstration that could be useful in terms of managing those peak flows that we spoke about that are a symptom of climate change. So we spoke about the equalization tank. So what does that essentially mean? It's a holding tank that's balancing out that diurnal flow peak that we saw earlier in the presentation. And so the volume of this tank is really a variable influent flow, which is according to that diurnal flow, but a consistent flow is pumped out to the downstream process units. So this tank's volume is going to change daily through this pattern, but it means that all your downstream process units can benefit from the consistent flow that is being pumped out. So that helps to protect against a peak energy consumption in your blowers or airflow or aeration units. And it can then also reduce the sizing of those units, which is also helpful on a capital cost point of view. Another example that I mentioned just in the demonstration that I wanted to just show in a bit more detail was the bypass tool that we've added recently. And there are three options for this bypass. You could take it from before the primary treatment all the way through to disinfection. And this is, you would do, for example, if you have a really big rainfall, this is your one day of the year where it rains so much that your wastewater treatment works can't actually manage the flow. And I think this happens in a lot of cases. There's always that one day or 1 hour, and bypasses are often installed. And so this is an example of that. And at least then you're still sizing your disinfection for the treatment of that ultimate peak flow, and not letting it discharge without any disinfection. But effluent limits and environmental impact limits are getting stricter. And so many situations now, it is mandatory to at least provide primary treatment in those situations of ultimate peaks. And so then maybe the bypass number 3 option would be more applicable, where you're designing your primary system for that peak flow and maybe bypassing it just before the main biology or secondary treatment out to disinfection. We've included this bypass option number 2 as well for other situations. What you can also then do with this bypass is run 2 parallel plants. Maybe you half the plant is treated with a conventional activated sludge and half the plant is a membrane bioreactor. You'd like to model how to upgrade both of them. You could use these bypasses and model the plants separately, combine the projects afterwards. So this bypass adds a lot of flexibility in terms of design in the Transcend design generator. And then just to end off, I've done a little mini feasibility study just to show that we could run 5 projects. I've run here 5 projects with very similar inputs, but just 1 or 2 differences. And it's very quick to compare these outputs. So normally it would take 8 or 9 hours to get some of these outputs, maybe just the process design figures per project for an engineer. And these were all created yesterday, and I put them in this table this morning, so it didn't take me very long. So this is the beauty of the tool. Just a quick summary here. I used a conventional activated sludge plant with the flows that you see above. So these are similar to the ones we used in the example, and influence and effluence as shown. And I just wanted to highlight what these temperature and flow tools can change for you in your projects. So if we increase the temperature by 10 degrees, you'll see here the peak airflow. The peak airflow is increased by that increase in temperature, and that's going to result in a higher airflow with a lower density of oxygen in it having to be produced. And the power consumption here is average, so you don't see it there, but you will see it in the peak power consumption increase there. The third project here is if we include flow equalization. So that's reducing the peaks. The reactor volume stays the same because it's designed for average, but you'll see the peak airflow is decreased. The power consumption is also decreased slightly. And then if we look at the fourth project there, it's got a primary filter and bypass. So that's using that bypass number 3 from the previous slide, where we're going through primary and then bypassing secondary to disinfection. And here you can see the reduced organic load from the primary treatment results in a smaller reactor, a much lower peak flow of air, lower power consumption, but we have the downside of a higher sludge production. Now we have primary sludge and secondary sludge to manage. If we look at a completely different treatment type, a sequencing batch reactor, for example, much bigger reactor volume is required, but we've got much lower OPEX, so power consumption and sludge production. So if you have the space and the capital cost available for that increased reactor volume, that might be great over the long run in terms of saving in OPEX. So just a couple of examples of how you can compare things, temperatures, flows, treatment types. There's a lot of options to compare, as Remy mentioned at the beginning, which is very important.
Thank you so much, Rudy. That was awesome. We have one question in the chat. What is the reject water treatment, a pumping step or a biological step?
The reject water is if you don't include the sludge treatment as a design step in the tool, then you can specify what reject water is coming from your sludge treatment. Maybe you have your own sludge treatment already and you don't want that to be considered. It is still important in the design of your treatment plant to consider any supernatant. That's what we call it in South Africa, but reject water may be more common, and that will return into your treatment system.
Thank you. All right, we'll hang on for a few more minutes if there's any other questions. Otherwise, thank you all for joining. Thanks, Anne-Marie. Good to see you. Yes, we will. This has been recorded, so we will be sending out the recording to everyone. Thank you all. All right, Rudy, we have another one. Zahir was amazed to see that SBR has 20% less sludge generated. Are these the same sludge ages in the scenarios?
That's a good question. The sludge age will be a little bit different for the different biologies. So the system will adjust as required. I can check for you quickly. Just give me 1 minute.
Thanks, Rudy. All right. Oh, Hani, sorry, I missed your message up at the top. So is this applied only for municipal wastewater? So right now, municipal wastewater is kind of our bread and butter. We have some capabilities to do some industrial wastewater as well within our configurable version. So that's on its way.
So just to answer on the previous question, there was a longer sludge age on the SBR project. It is possible to control that and make sure that it's the same for all the projects if you're wanting to compare. As we saw in the design generator, there is an input for sludge retention time so that you have all the main biologies using the same amount. I didn't do this in this example, so it's not a great comparison on that note.
Thank you, Rudy. Zahir, I hope that answered your questions and happy to follow up on that if needed. All right, well, if there are no other questions, we will give you guys a couple minutes back in your day. Thank you all for joining. Have a good one.